All right, so we're in the same document that we did yesterday, right? So today we're learning a couple of new factoring methods. You just need to know which method is good for which situation, okay? No one's going to tell you that. They're just going to give you a problem, or you're going to come across a problem, and you've got to know strategically which one's going to be best. So we already did the first few yesterday, and we're picking up with, let's just do number 3 just for review, right? The first thing that we should check for when we're factoring is what? Yeah, greatest common factor. So we pull out that greatest common factor and we get x squared. 3 divided by 3 is 1, so negative 1x, negative 6. And then we can go straight to our table, right? So we're looking for multiples. I call it an MS chart. Multiples of something that have a sum of another number, right? Multiples of the last number here, negative 6, that add up to be the middle number, negative 1. Okay. So multiples of negative 6 are 2 and 3. Where's the negative going to be, on the bigger or the smaller? Yeah, on the bigger. So if they add up to be negative, well then I know that the bigger one has to be negative. So negative 3. 2 times negative 3. Hey, that looks like the right pair. Okay? And so because we are starting with 1x squared, right? We were able to divide the 3 out. Then we can go straight to our factors, our parentheses. Still keep the 3. And then we have x and x, because it's x squared, right? If we FOIL these back together, we would get x squared. And then plus 2 and minus 3, and then we're done. So those are the factors. How many factors does this expression have? 3. The one we pulled out in the very beginning, the GCF, and then these 2 binomials, okay? And if I FOILed and then distributed, I would get right back to the beginning. Okay, so you can always check your work by re-multiplying all of the parts back together and see if you get to where you started. Okay, so that's number 3, just a review. And then look down at number 4. We skipped this one yesterday, and I want to talk about it today. So today's lesson is titled on my calendar, Factor by Special Products. Special products. Now, I've tried to synthesize the methods together so that you don't have like 6 different methods to remember. You've got as little as possible. So I'm sticking to my 3 methods with a caveat on this one. So first, we should divide a greatest common factor out. Divide the 2 out. Each of those is divisible by 2. We get 2x squared minus 9. Okay. And some people will say that this is divisible by the difference of perfect squares. And that's totally true, 100% true. But for some reason, people have a hard time recognizing that. Like if you're not really, really quick with your times tables or your square roots, then you might not recognize that. And so I always tell people, hey, if there's a missing term in the middle, right? We've got an x squared term, and we have a term with no x, but usually there's one in the middle, right, with just 1x. Let's put it in there without changing the value of the expression. X squared plus 0x minus 9, right? That looks more familiar. That's in our standard form. That's the form that we usually use the table in. We use the table here as well. So we're still looking for multiples that, or numbers that multiply to be that last number and that add up to be the middle number. So if they multiply to be a negative and they add up to be 0, well, they're going to be the same number, right? A positive and a negative of the same number are going to add up to be 0. So what 2 numbers do we have here that multiply to be negative 9 and add up to be 0? Yeah, 3 and negative 3. 3 and negative 3. And so we can go, again, because we start with 1x squared, right there, that's a 1, so we can go straight to our factors. X plus 3, x minus 3. Okay. If you remember the difference of perfect squares and how to factor that right away, you can skip this process. You're welcome to. It won't be any points off or anything like that. But if you're not good at recognizing that pattern, this is a consistent method you can follow. Okay, so why don't you try number 6 on your own? Try number 6 on your own. And I'll pause it, put my answer up there in a minute. All right, so hey, hopefully you divided a 3 out. Divided the 3 out here, so 3 x squared minus 100, okay? And then if you followed my method to the left here, you put a 0x in the middle. You're missing that b term, that middle term, the x term, so you put a 0 in there to hold its place. And that doesn't change the value. You basically are adding 0 to something. It's not changing the value of it, but it is a form that's more convenient. So you can find factors of negative 100 that add up to 0, which of course is 10 times 10, one of them being negative. So that's our pair. So we go 3, x minus 10, x plus 10. Okay. Any questions on that? All right. One more method. So there's another pattern for 9 and 10 that you can follow. And I don't go through it. If you want to know it, I can show you after the notes if you want to. But in my experience, it's harder to remember than it is helpful. So it's like the work is not worth the payoff. You can use group and split on those. The method we talked about yesterday, group and split. So, but if you really care, if you really want to know the shortcut for 9 and 10, I'll show you, and then you can decide later if you actually think it's a shortcut or not. But we do need to talk about 11 and 12. So 11 and 12, those are different, right? What's different about them? They're cubed. They're not squared. They're cubed. Okay, so we have to factor these differently. So we call this the sum or difference of perfect cubes. So a perfect cube is a number that is the product of a smaller one by 3 times. So like 3 times 3 times 3, that's 27. 27 is a perfect cube. 2 times 2 times 2, that's 8. 8 is a perfect cube. 5 times 5 times 5 is 125. 125 is a perfect cube. Okay, you see the pattern? So like squares, perfect squares, these are perfect cubes. And so if we have the sum or difference, adding or subtracting, of perfect cubes, then we can use this method. And this is a perfect cube. X times x times x is x cubed, and 2 times 2 times 2 is 8. So these are perfect cubes. We can use this method. The method you're going to use is called soapbox. That's just a clever name to help you remember some of the pieces. And here's how you do it. You are going to draw 5 boxes, 2 on the top in a row, and then 3 below that. Kind of like the Olympic rings, right, in the Olympic logo, where 3 are on the bottom and 2 are on top. And the square root of the first perfect cube, cube root of the first perfect cube is going to go in the first box, and the cube root of the second perfect cube is going to go in that box. Okay, so I'm pulling 8 and x cubed. I'm taking their square roots, and I'm going to put them in those boxes. So what is the cube root? I keep saying square root. What's the cube root of x cubed? Yeah, x. What is the cube root of 8? 2. Okay. And then the lower boxes are going to be filled in by think of it as cascading down. Like these upper boxes are going to fill in the lower boxes, okay? So the middle one has access to both the x and the 2. And so it's going to be, it has access from the x and the 2, so it's going to be 2x. right? Because it's being filled in by the x and the 2. The outside box, it only has access to the x out here on the left. So it's going to be filled in by x and x again, which is x squared. And then the box on the right, well, that's only being filled in by the 2, so it's receiving a 2 times a 2, which is 4. Okay. And then the last thing is to fill in signs here. So we have to have signs in between all of these boxes. We need a sign here, here, and here. And that's going to come from our acronym SOAP. So the signs follow SOAP. S for same, O for opposite, and AP for always positive. Same, opposite, always positive. So when I say same, I'm saying what was the original sign? It was plus. You see that? Plus up here, so the same sign will be plus. We'll have a plus right here, plus. Opposite is opposite of whatever the original sign was. So the original sign is plus, so opposite is minus. We'll have a minus there. And then always positive, well, that's self-evident. It's always positive at the end there. Okay? And this all may seem very arbitrary, but this actually gives you your 2 factors. One of the factors of this expression is the top row, x plus 2. And one of the factors, the other factor of this expression is the bottom row, x squared minus 2x plus 4. So that's the soapbox method. I don't know of a more memorable method to factor sum and difference of perfect cubes. If you find one, let me know. Because all of this to me feels like just kind of like magic, and there's not really... I like math where there's a reason for every next step, and that's one thing I don't like about this method. So if you find one that's better, let me know. But this one works. And a common question I have is, well, can't you factor this quadratic at the bottom, like this thing down here? No, you can't. If you started with the sum or difference of perfect cubes, you're never going to be able to factor this right here. You're always going to be done. Okay? Okay. So if you feel good about that, you're welcome to jump into the homework. If not, I'm going to do number 12, another example of this, for those who want to see more. Okay? Any questions before I jump into number 12? Okay. So number 12, just like any factoring problem, we're going to divide out a common factor. So I'm going to divide 3 away. 3. And I end up with x cubed minus 1. And I should recognize that this is, I'm not going to put a 0 in here, right? I'm not putting a 0 in the middle here because this is not a squared problem. This is not a quadratic. This is cubed. And so I see x cubed is a perfect cube. 1 is a perfect cube. What times itself again is 1? What number? It's 1, right? So it was kind of a cluttered question. What number times itself again is 1? 1. 1 times 1 times 1 is 1. So each of these are perfect cubes. There's a minus in between them. That's fine. And so I know I'm going to have to use the soapbox. So I'll draw my boxes. And then the cube root of the first perfect cube goes in the first box, x. the cube root of the second perfect cube is 1. So I'll put a 1 there. Okay. I'm holding off on the negative right now. Okay. I know that the cube root of -1 is -1, but I'm going to deal with the signs at the end. Okay, that SOAP acronym is going to help me deal with what to do with that negative and how it impacts the signs down here. So hold off on the negative right now. Just take the 1. Cube root of 1 is 1. And then fill in those bottom squares. Okay, so the middle square is receiving both the 1 and the x, so it's 1x. The far left square, it only gets x, so it gets a double dose. X times x, x squared. And the far right, it only gets the 1, so it's getting a double dose. 1 times 1. And then the last step, use your SOAP box to fill in the signs. Same, opposite, always, positive. SOAP, same, always, opposite. Same, opposite, always positive. SOAP. So the same sign, well, the sign originally was negative, so the same sign is a minus, same as the original. Opposite, the opposite of the original sign is plus. And then always positive, well, that's always positive. So my answer is x minus 1, the top row, and then the bottom row, x squared plus 1x plus 1. Okay. And just for clarity, I think Pearson might ask something like this. That first factor, that's called my linear factor. Because if I graphed it, it would make a line, right? And then the second factor here, if I graph that, that's a parabola. So that's called my quadratic factor. And then I did forget one little thing. What did we do in the very beginning of this problem for those who are following along? Yeah, we divided out that 3 in the beginning, right? This 3. Don't forget it, like I did. 3. So just for clarity, this is also a linear factor, because if I graphed it, it would be a line. Okay, so that's it for the notes. Jump into the homework if you haven't already. And we have a quiz over this on Monday. Quiz on Monday. All right, this and the other things that we've covered this week.